You don't want to how do you register for class? You don't have enough for seniors and all. You're not even going to be able to register that's what I call it. The ER program, they actually only use the one document. So you see a file. Who is that? What about a PS2? Oh. What? Hey, you guys think we're going to do our final? Probably won't happen. Yeah. Do we have our how long was that? It was over a month. Networking now? It was like, it's not a month. No. I mean, 3 weeks is about a month. Just throw it out there. Yeah. What? Okay, so it was on that month. My initial over.
All right. So we're starting this new chapter, chapter 6. It's on applications of Fourier transforms, and it starts with a discussion of filters. We'll talk about some basic filter design here. But typically in the filter design process, you're given the filter specifications, and you have to understand what that means. Part of that, they're typically given in perhaps a graphical form, and what's known as a Bode plot. You may have seen that in circuits too. But we primarily break filters down into 4 basic types of filters, depending on the frequencies they pass through the filter and the frequencies they eliminate. Now, generally, what we want to do is pass through the signal of interest and filter out perhaps noise or maybe interfering signals. And so the type of filter required in any application depends on the frequency content of your desired signal, and then also the frequency content or frequency location of the noise or interfering signal. So what's shown here are the 4 classical types of filters. The one in the upper left is called a low pass filter. It's designed to actually intended to pass through low frequencies and filtering out high frequencies. Of course, that's all relative. You know, we really have to define where, you know, kind of the corner of this thing is. Now they show here this blue line, which is kind of the typical response of what we call a first order filter. Maybe just a simple, made out of a simple, just a resistor and capacitor, or simple resistor and inductor. Sometimes they're sufficient. They do good enough. Ideally, we often want maybe this filter that's shown as this rectangle here that has that very sharp edge and you know, a flat top for all frequencies below this WC filter or WC frequency. That's what's known as an ideal low pass filter. Okay, we can't really build a filter that has that nice a response with that steep edge and completely filters out everything above omega C while passing everything below omega C. But by using higher order filters, we can get better and better, you know, approximations to this thing, you know, that look more and more like the ideal. Of course, higher order filters require more capacitors, more inductors, more resistors, and are consequently more expensive. Okay? The more components you use, especially, and that's a consideration if you're going to mass produce some sort of object. So this is what's called a low pass filter. It has, you know, a maximum value here. This is actually the magnitude response of our frequency response. So it's the magnitude of our frequency response. It's what we're plotting here. We classify filters based on their magnitude response, kind of ignoring the phase response. Now the phase response is important. I think he's got shows some has some illustrations in your textbook where he's done some image filtering. And in one case, actually kind of ignoring the effects of the phase response and got some disastrous results. But so the phase response is important, but we classify filters primarily based on their magnitude response. So this is a low pass filter. You know, a high pass filter passes through high frequencies and filters out low frequencies. You know, band pass filters, this is a band pass filter. It's designed to pass through a certain range of frequencies. So, you know, kind of the classic application here is for radio and television. If you want to pass through a particular channel or station, or listen to a particular channel or station, you know, you would pass through that corresponding frequency. So, like on your FM radio, you know, you want to listen to 98.6 megahertz. You want to pass through 98.6 megahertz while eliminating 98.8 megahertz and everything higher and 98.4 megahertz and everything lower. That's not quite actually how it's done in practice, but you'll learn it's done using a technique called a super heterodyne receiver, which you'll learn about next year. But it's a good way to conceptually think about how it operates. You know, it passes through certain frequencies, and certainly the bandpass filter is a component of the super heterodyne receiver. Okay. And its purpose there is actually to pass through the station we want to listen to while filtering out others. And then the fourth type is a band reject. This is typically used where you have an interference at one particular frequency, and you want to eliminate that interfering signal. Or maybe you live right next to a television transmission tower or radio transmission tower, and that frequency is kind of saturating everything else in the house, all your other communications equipment. You may be able to suppress that by adding a band reject. It's sometimes also called a band stop filter. So, some of the terminology here, the pass band is the width of the frequencies that are passed through the filter. And it's, you know, with the ideal filter, it's well defined here, the edge. For our, you know, the classic first order filter, we take to be the width. And it really kind of has infinite width because it approaches that omega axis asymptotically. We define to be the width the frequency at which the response is down by a factor of 1 over square root of 2 from the peak response. Okay, it seems like an arbitrary thing, you know, why not? Why 1 over square root of 2? Why not 1/2 or, you know, whatever. 1 over square root of 2 in the amplitude response corresponds to 1/2 the power. Okay, so this is called the corner frequency, the cutoff frequency, the half power frequency. Those are all different names you'll hear applied to that corner frequency. Again, it's not a sharp corner there. It's just the frequency at which the response is down 1 over square root of 2, or 0.707 from the peak response. Now, the pass band of a high pass filter is infinite, right? It goes from the corner frequency and then passes all frequencies above that. Whereas the pass band or bandwidth of the low pass filter is well defined. It's actually omega C. Now, for a high pass filter, you may also talk about the stop band. And it's well defined for a high pass filter, but infinite for a low pass filter. And for a band pass filter, you've got 2 edges to work with. But again, we define the corner frequency to be the frequency above and below the peak response frequency, where the response is down 1 over square root of 2. And so there are 2 frequencies on either side there. This omega 0 is for these are typically built with RLC circuits. This omega 0 is also called the resonant frequency. And you know, we use similar terminology here for the band reject filter. So different filter types, and we looked at those and just by looking at this figure. What we want to concentrate on is actually drawing this magnitude response. So let me give you some notation. We'll define M of W to be the absolute value of our frequency response. That's not necessarily common in a lot of textbooks. You'll just see it labeled as the absolute value of the frequency response. And then, so this is the magnitude response. And then here he defines phi of omega to be the phase response, the angle of a frequency response. And what's plotted there are the magnitude responses of 4 different filters. So again, what may be given is, you know, a graph something like this. And from the graph, you pick off the omega C, the corner frequency. And then you can actually use the slope here to determine the order of the filter as well, to lead you in the direction of the filter design. Now, these may be plotted in linear units, like as shown in that graph, but typically the magnitude response is plotted in decibels or dB instead of just plotting the absolute value. Okay. And that causes the plot to look much different. So mdV of omega is 20 log base 10 of m of omega, or 20 log base 10 of the absolute value of our frequency response. Now, so if I have, this is m of omega, or HEB of omega. It takes a little while to get comfortable with dB, but if h of omega is 1, what is, so this is also m of omega, or mdB of omega. What is the corresponding response in dB? You know what the log of 1 is? Log base 10 of 1? The log base 10 of 100? It's the number of zeros in like any power of 10, right? So log base 10 of 100 is log base 10 of 10 squared is 2. So log base 10 of 10, that would be 1. But since we got this multiplication by 20 here, so 10 would be, what I say, that would be 20 dB. 100 would actually be 40 dB. 1 is 0 dB. Now notice it doesn't matter here whether it's plus or minus 1. The plus or minus actually comes in with regard to the phase angle. This is the absolute value. So plus 1, minus 1 would have the same dB value. 1,000 would be 60. Notice it, as our gain goes, our frequency response here goes up by a factor of 10. Corresponding change in dB is just 20 dB. In general, 10 to the capital N power is just 20 times N. So this is actually, remember, this is the output over the input. So a linear gain of 1, where the output is equal in amplitude to the input, that means a gain in dB of 0. So a 0 dB gain doesn't mean no gain. Actually means the output's the same amplitude as the input. Positive dB values means that the output is greater than the input. A 20 dB gain means that the output is 10 times the amplitude of the input. Some other common ones you run into, square root of 2 is approximately 3. You can plug that in your calculator. 20 log of square root of 2 is approximately 3. And then 2 is approximately 6. 4 is approximately 12. 2 to the n is approximately 6 to the n. So 8, which would be 2 to the third, that corresponds to about 18. The powers of 10 are exact. These are actually just pretty good approximations, okay, if you plug them in your calculator. So you can also have like a gain of 0.1, and you would have that typically out here in the stop band. That just means the output's 1/10 the input. Okay, so now instead of providing gain, it's attenuating. So our filters here, over some range of frequencies, they may be providing gain, but over other ranges of frequencies, they're attenuating. 0.1 is actually minus 20 dB. 0.01 is minus 40 dB. 0.001 is minus 60 dB. It actually still follows the same rule. 0.01 is actually 10 to the minus 3, right? So 20 times minus 3 is the minus 60. And 1 over square root of 2 is minus 3 dB. 1/2 is minus 6 dB, and so on and so forth. Now, usually in the filter design process, what you may be given is what's called a Bode plot. It's a special plot of the magnitude response. This technique, this Bode technique, provides a very quick and easy way to go from the frequency response to a graph with just a pencil and paper without having to resort to a computer. So it used to be really heavily used, this technique. It's easy to get. We've got tools like LT-Spice or Octave that can easily generate these Bode plots for us from our frequency response. I'll show you how to do that. But so you could argue, well, why do we still go through this hand technique? Well, you don't really have to for the analysis. But for what we're ultimately wanting to do is actually go from the graph to a circuit. In order to be able to do that, you really have to understand how to produce the graphs. And to develop that understanding, we're going to actually draw some of these by hand using the pencil and paper technique. And hopefully with some practice, you'll get pretty good at it. And then we can compare to the graphs that are created with MATLAB or LT-Spice. So say we've done, and today I'm not going to start with the circuits. I'm going to actually just give you the transfer functions to start. So what we've done, I think this is maybe one of the problems from the end of this chapter. This would be a first order filter. Certainly by looking at it, we can't really tell if it's or I can't, maybe you can, whether it's a low pass or a high pass filter. Actually, you probably can. At low frequencies with omega equal to 0, this is going to be like 1.6 over 10. It looks like it has a gain of 1 at low frequencies, right? With omega equal to 0. As omega becomes really, really, really large, the j omega terms are going to dominate these constant terms, and this is going to approach 2. Is that right? So at very large frequencies, it looks like the gain of that term is going to approach 2. So we'll see. We'll draw and see. The first step is to actually, we can do this pretty easily with a computer or even your calculator. We need the square root of the sum of the squares. Again, the j, you don't square the j. That would be the magnitude response. It's just a real function of omega. There are no j's in this. So you could plot this pretty easily, the magnitude response, pretty easily on your calculator. You can plot it in dB, just 20 log of this. The phase response would be, and it's the imaginary part of the real part, so it'd be 2 omega over 16,000, and then minus the angle of the denominator, which is omega over 1,000. And pretty easy to plot that on a computer, and we could see what type of filter it is, but we're going to use this Bode method. So the first step is actually express the frequency response in standard form. And that means we want to express any first order terms like this, 1 plus j omega over some special value, some constant value. So starting here, all we have to do is factor out the 16,000 from the numerator. So I'll have 5 times 16,000. And so I'd have 1 plus j omega over 8,000. And then I'll factor out the 1,000 from the denominator. 1 plus j omega over 1,000. This constant in front is just 10. Actually, now in this form, it's actually a little easier to see. I think I said the gain earlier at omega equals 0 was 1, but I did my math wrong. It's a little easier now to see, at least in this form, with omega equal to 0, the gain at low frequencies is actually 10. At least if I've done my math correctly now. At very high frequencies, when these terms dominate, we'll have omega over 8,000 divided by omega over 1,000, that would be 1/8. So very high frequencies, the gain is actually 1/8 of 10. So it looks like it's going to be a low pass filter. So the next step is draw the components of HDB omega on log paper. This is actually Similog X paper. Okay, so before we do that, I'll hand this out to you, but $20 log of the absolute value. Well, the log of a product is the sum of the logs, right? The log of a ratio is the difference of the logs. So this will become, I'm viewing this as 10 times this divided by this. So this becomes 20 log of, again, I've got the absolute value here. The absolute value of 10 is 10, plus 20 log of absolute value of 1 plus j omega over 8,000 minus 20 log of 1 plus j omega over 1,000. Now, in any particular problem, you might have a couple of first order terms in either the numerator or denominator. These would all correspond to actually, having real poles and zeros. And the other case that we dealt with are the second order terms, where we've got a complex conjugate pair of poles and or zeros. But this is the simplest case, and so we're going to tackle it first. So what we're going to do is draw these terms individually, and then graphically add them together. It's not as hard as it may sound. But so the 20 log of 10 term is just a constant 20. But now we've got two terms that look like this generally. 1 plus j omega over omega c. In one case, omega c is 8,000, and the other case it's 1,000. But the other two terms, we're adding the term that's like that in the numerator, subtracting the term that's like that in the denominator. Of course, this is 20 log of 1 squared plus, or just 1, plus omega over omega c squared to the 1/2, right? That's what that looks like. Now, to a pretty good approximation what that term looks like, and we'll do this on log paper. So on semi-log paper, we'll find this point omega c. But on semi-log paper, 10 omega c is the same distance above omega c as 100 omega c is above 10 omega c. Okay, this distance is the same, as would be, this would be omega c over 10 and omega c over 100. So they're equally spaced here in what are called decades of frequency. A decade of frequency is a factor of 10. So a decade above 200 hertz is 2000 hertz. A decade above 2000 hertz is 20,000 hertz. A decade below 40 hertz is 4 hertz. That's the terminology. It's not adding or subtracting 10. It's multiplying or dividing 10. The other term that you'll hear is an octave. Now, what do you think an octave would correspond to? Multiplying or dividing by 8. That would make sense, right? Because an octave, octopus. But it actually comes from music. And there are 8 whole notes, I guess, in what's called an octave in music. I think 12, I'm not a musician, 12 semitones or something, but 8 whole notes. An octave, though, actually corresponds to a doubling of frequency. So the 8 there comes from the 8 notes. But as you go up from C, the note C to the C that's an octave above, it's actually doubling the frequency. So an octave corresponds to a doubling. So if you hear the term an octave above 400, that's really 800 hertz. An octave above 800 is 1600 hertz. So it's a little confusing. But the approximation here is for, you can think of this as, I'll pencil in here 1,000. Well, we're dealing with that 8,000 term. That's the positive one right now, right? So I'm trying to do this in general. But for frequencies omega less than this omega c constant, we're going to pretend that this term is small compared to 1, okay, to do this graph. So essentially, we're going to ignore this term for omega values to the left of omega c. And so what this reduces to is 20 log of square root of 1, or 20 log of 1, which is 0. That's really easy to plot. Okay, that's just this line. Okay. And so that's just this 0 for frequencies to the left of this omega c frequency. We're going to do something similar, but different, for frequencies greater than omega c. When omega is greater than omega c, this term is going to be greater than 1. So we're going to ignore this term. So for frequencies for omega greater than omega c, 20 log of 1 plus omega over omega c squared, the 1/2. I'm going to say that that's approximately 20 log of, this term squared, then the square root of that. Okay, so we effectively just ignore the 1 and say for frequencies to the right of omega c, we're going to approximate our frequency response using this simpler equation. Okay. Now that equation actually is really simple if we work in decades. So when omega is 10 times omega c, so here, a decade above omega c, this will become 20 log of 10, which is what? It's 20. Okay. So this would be 20 dB. When omega is 100 omega C, at this point, what does that evaluate to? 20 log of 100. That's 40. So that would actually double. Okay. What do you think it is at 1,000 omega C? 60. Okay. So this actually goes up at a 20 dB per decade rate for a term like that. Okay, so it's a straight line. That's the key thing. And it would go up forever. So to draw these terms like this, it's just these two pieces. A line, that's at a dB value of 0 to the left of omega C, and then another straight line that goes up at a 20 dB per decade rate to the right of omega C. Okay. Now this 20 dB per decade rate is also the same as, very approximately, 6 dB per decade. Sometimes it's when you're drawing these, it's helpful to, sometimes you have to work in terms of octaves because you run out of paper and you've only got a doubling of frequency or something like that. Now, here we've added this. The other, sometimes we're subtracting. If we subtracted it, it would just go down at a 20 dB per decade rate. Okay, that's what that last term does. So now we're going to try and really what we're doing is going from this standard form to the graph. And I'll show you how to do that right now, but I'm going to pass out this paper first. Actually, should be enough for everyone to get like 2 pieces here. So take 2 pieces and pass it on. Everyone have? Okay. I can save any for myself. Just a second. So it's got a little set of arrows down here that should be on the lower left-hand corner of the page. Okay. So that's just a guide, so you're not using it upside down or something. So on these graphs, the bold lines are a decade apart. Now, what we need to do are identify our critical frequencies and try to set up the scale so that all these critical frequencies are somewhere near the middle of the graph. So our critical frequencies are 1,000 and 8,000. So I'm going to just label this one to be 1,000. Okay. So this would be 10,000. This would be 100 actually. This would be 100,000. Now the way this graph works is actually this next bold line would be 2,000. So the bold lines here are 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, and then 10,000. Some of them you have multiple dividers. What's really going on here on this log scale, as we go from log of, let's say, log of 1 to log of 10, if you take log of 2 turns out to be a third of the way between 1 and 10, log of 1 and log of 10. I mean, if you type log of 2 on your calculator. So this would actually be 1,000. This would be 1,200, 1,400, 1,600, 1,800. But the bold lines are, 1,000, 2,000, 3,000, 4,000. Here between 4 and 5,000, we just show 4,500. Between 5 and 6, it's 5,500. But the lines get closer and closer together here. So this is 8,000. There is no dash line between 8 and 9,000, or between 9 and 10,000. Okay, is that, everyone gets that, how this is laid out? It's a little bit unusual on that horizontal axis. So this is called semilog X. The x-axis is laid out in a log X scale. It's called semilog X because the y-axis is a standard linear scale. Okay, so you get paper that's semilog Y, where the y-axis is logarithmic and the x-axis is normal. Or you can get log-log paper, where they're both laid out logarithmically. For our Bode plots, we want semilog X. Okay. Now, the other thing that you have to do is kind of lay out the vertical scale. Sometimes you end up making some erasures here, trying to guess. We've got, so I'm gonna label that line 0. Could be any one of these bold lines. But now I'm going to mark my critical frequencies. The 8,000 is in the numerator. I'm going to mark that on my 0 dB line. 998. Here's my 0 dB line. I'm going to mark that with a circle in the numerator corresponding to a pole frequency. I'm sorry, a 0 frequency because it's in the numerator. And then the one in the denominator is at 1,000, so I'll mark that as an X. Okay, any questions about that? Now what do the pieces look like? Well, let me finish off this. Again, you could lay this out, 5, 10, 15, 20. I'm going to label this like -20, -40. So that would mean this is 20, 40. Okay. Not really sure what vertical scale. I do know that these things are trending at 20 dB per decade. So what does the pole term do? Okay, it's that. And then here's where it's helpful to have a ruler when you're doing these things. And then now this goes down at a 20 dB per decade rate. Okay, it goes down because it's a pole term. It's in the denominator. So it would go like that. Okay, 20 dB per decade. If you'll notice, well, let's see, 6 dB, so this is 10, this would be 8, this would be 6, so 6 dB is right there. That should correspond to a doubling, so 1,000 to, it looks like I'm slightly off with my line. It should actually go 6 dB, 2, 4, 6. It should actually go right to that point. Okay. And if you lay that out with a straight edge, you should have that. But this is going down at a 20 dB per decade rate, minus 20 dB per decade. Let me see if I can get another color. The zero term, remember it's this. Okay. Now when I get out to the zero, it's going to go up at 20 dB per decade. Okay. So here it's 8,000. Out here at 80,000, it's going to be 20 dB higher. So that'd be right there. So I could lay my, if I had a ruler, I screwed it up right there. I do better this time. Okay, and that line would continue forever. And then the other piece here is my constant, the 20 log of 10. Now it's 20 dB. And that is 20 dB forever. Okay. The last piece is to graphically add these things together. Now, you start over here at the left. I just got the constant term. The other two are zero. Right? So to graphically add them, I'm going to follow my constant term. Okay. Out to where I get to my first critical frequency. Since I'm just adding, now I'm going to start going down into 20 dB per decade. So I'm actually just going to draw a parallel line, parallel to this negative 20 dB per decade. So this really would take me to this point, okay? And then that would continue on forever, right? 20, yeah, it doesn't look parallel, it should be parallel. This goes down 20. And that would end up right there. So I guess maybe it's just I'm standing too close. Now that would continue like that, except when I get to this frequency, it now goes up at 20 dB per decade. So to the right of this frequency, what's going to happen? It's going to level off, right? Now, what this gives me, or should give me, well, how would we classify this as what type of filter? What do you say? Low pass. We've got higher gain at the lower frequencies. And this appears to pass through frequencies up to about 1,000. The true response would actually be, you know, if I plotted this, it's going to look pretty good. It's going to be off by 3 dB here. This 1,000 is actually the 3 dB frequency, or the corner frequency. It would be the cutoff frequency of this filter. Similarly, the response here would be a little bit above that. But this, if I actually plotted the true response in dB, it's going to match up pretty well. But the corner frequency of this low pass filter is 1,000. Now I've laid this out in radians per second. We've drawn this in omega instead of hertz. So the cutoff frequency is 1,000 radians per second. It also has a 20 dB gain at low frequencies. And it looks like, you know, the way I've drawn it, what I say, this is about a 2 dB gain at high frequencies. So if we come over here, you know, certainly at low frequencies, H of 0 in dB is 20 log of 10, right? With omega equal to 0, that's 20 dB. H of infinity, a dB, is 20 log of, here, if I let omega become infinitely large, ignore the one terms, I'll have omega over 8,000 divided by omega over 1,000. So that would be 1/8 times 10. So I'm going to get 20 log of 10/8. Someone want to do that on your calculator? It should be, I'm guessing, pretty close to 2 dB if I've drawn that figure at all correct. Pretty close to 2 dB. So the figure gives us a lot of, with a little practice, you can whip these things out pretty quickly. There's a technique for actually doing the phase response, but I'm not going to do that. He talks about that in the book. The other type of term you might run into is a second order term, which you can put in this form. Actually, it would be omega over omega c squared. Here at omega c, the only difference would be you would go up at a 40 dB rate because of the squaring, or down at a 40 dB rate for the second order terms. It takes a little practice to get used to this, to help get proficient at drawing these things, and that's why I give you homework. So you've got some homework problems assigned today, which I put up a link to this PDF paper, so if you need to print out more, but I think you've got enough there for the homework problems. So see you Wednesday. Yeah. We do it now.
I have it all laid out.
Okay. I'll just pull it up here.
Yes.
Maybe sometime I could. Pretty sure.